Welcome to CS 101, Scientific Python, Lecture 19 on numerics and brute force. We're going to be starting a 3-lecture arc on optimization. Optimization means finding minima or maxima in mathematical problems, which often have many different unknown variables. This can get quite complicated, but optimization problems form the solution to many problems in physics, engineering, and other areas. This time we're going to look at applying a brute force or comprehensive search to solve problems relying on multiple dependent variables with or without constraints. We're going to look at some of the other features that are available in the library called iter-tools or iterator tools, things for use with for loops. We're going to talk about some of the things that distinguish the kinds of problems that we solve when optimizing. And then we're going to look at a library brute force algorithm, scipy.optimize.brute. Given a particular problem, if you can exhaustively calculate the fitness of every possible solution, then you can solve the problem optimally. This is referred to as a brute force solution because it simply throws computing power at the problem until it is solved. For instance, let's consider searching for a password. Here we've defined a function, checkPassword, which accepts a candidate password and compares it to see whether or not it is the right password. Now, this is a really low security way to manage passwords, and certainly any service that you would ever use would hopefully do something much more sophisticated than this. But it will work for illustrating our point. In the lower half of this code, we've defined all of the characters which can validly form part of the password. We're going to loop over each of these using iter-tools.product, which we'll talk about more in the future. But basically it allows us to take sets of AAA, AAB, AAC, etc. all the way through every possible combination of the characters in chars. We're going to join those together into a string. We're going to pass that to checkPassword, and then we're going to print it if we find the correct password. This is a brute force solution because it's going to try all of the different passwords that are possible in the solution space. So all 3-letter passwords that use these characters. If I run this, then we'll see that it very quickly finds pass. Now the challenge is that the search space explodes in size as we add more and more characters. In this case, we see that for the number of characters in the alphabet, the number of digits, the number of special characters added together, we can see that it's 86 to 94 characters possible per letter. This means that the problem gets very big very quickly, which is a limitation of brute force solution methods. However, generally speaking, unless the problem that we're trying to solve is convex, like a parabola, only a brute force search is guaranteed to find the optimal solution. However, the use of a brute force technique is not advisable when there are many variables. It becomes too expensive to solve with raw computing power. We must, in any case, define a figure of merit, some value which allows us to see how good a candidate solution is. Typically, this is the function itself, right? We define a function f. We say find the minimum of this function. F is our figure of merit in our language. It's the thing we're trying to find a minimum to. Typically, this is going to mean locating that minimum and returning the x or xy or xyz value at which that minimum occurs. The general problem we're going to be solving over the next few lectures is this optimization statement. Given a function f of x, where the underline under x means that x is a vector, possibly therefore several variables x, xy, xyz, find x equals x star such that f of x star is a maximum or a minimum. In other words, x star is our actual solution to the problem, whereas the field of x is simply a set of candidate solutions to the problem, and we examine each x for brute force. The goal is to search the domain for the x star which yields the optimum f of x star. In other words, the solution. There are many clever techniques for doing this. We're going to start with a naive approach, which is brute force. To do so, we'll look at a particular illustration in depth. Consider this problem. On vacation, you purchase a collection of n coins of varying weights and values. If you think about it, the size of a coin doesn't directly correlate with the value, so you have to keep track of both the weight and the value separately. When it comes time to pack, you find that your bag has a weight limit of 50 units. We'll leave this generic. But we can only take home some subset of these coins. Our problem then is, what is the best set of items to take on the flight? In other words, which collection within this full collection of coins maximizes our value while remaining within our weight limit of 50 units? First, let's set up that problem. Here we've imported NumPy. We've set a consistent random seed so that we can make this problem repeatable. If you use this seed, you will see the same outcome I do as I work through this problem. We're going to select n equals 10 coins. We're going to obtain the indices, or a number for each one of these, 0 through 9. We're generating random weights in the range 0 to 50, and random values for each coin from 0 to 100. First, we need to define a figure of merit. What is the thing that we're trying to maximize? Well, in human language, we're trying to maximize the value, but we have to stay within the weight limit. So value needs to be the most it possibly can be, while keeping weight under 50. If weight is more than 50, even if it's a higher value, it's a worthless solution to us. Here we've defined a figure of merit. It accepts a list of weights and a list of values. Starts with a total weight and a total value, so this is an accumulator pattern. It adds up the weights and the values. It checks to see if the total weight is greater than or equal to 50. If it weighs too much, we return 0, because a solution that's not a valid solution is no good to us whatsoever. Otherwise, it returns the total value. So this figure of merit is the thing that we're trying to maximize for any given set of coins. So weights and values, WTS and VALS, coming into this function, define that particular set of coins that is being evaluated each time we call F. Now let's go ahead and construct a solution to this problem together. In total, we're going to solve for all combinations. We're going to use iter tools, which you'll take a look at in the next block of this lesson. We'll set max value equal to 0 and max set equal to none. In other words, this is tracking what is the best solution we've seen up to this point. We need to keep track of the set of coins that yields this solution, max set, and the value that corresponds to f of max set, which is starting at 0 because any valid value will be higher than 0. Now let's try this naively first. For set in itertools.combinations, items, well, let's try all the pairs first. So if you'll recall, or if you jump ahead, you'll see combinations gives us every possible way of putting together each set of items that involves 2 items without repeating. So this will give me all of coin 0 and coin 1, coin 0 and coin 2, coin 0 and coin 3. When it gets to 0 and 9, it'll loop back around and give me coin 1 and coin 2, coin 1 and coin 3. So this represents all possible pairs of the coins. We'll set up WTS and vals as empty list to start. We'll go ahead and build up these lists by appending each of the units from weights and values that we generated randomly earlier. representing each coin. We'll calculate the value that it has each time through, and then we need to evaluate whether or not this is a better solution than any other solution we've seen up till this point. And we'll take a copy of max value and set. I'm going to add one more piece here. I'm going to print the value and the set that yields me the current maximum that I'm at. So when I run this, the first good solution it finds is the pair of coins 0 and 2, which combined have a value of 73.6. Then it finds coins 0 and 3 do better than that, and then it finds coins 3 and 4 do better still. All told, this is a way of checking every single pair of coins. Now we know that there's more than just pairs going on. So we also have to reset this code and look at trios of coins and quartets of coins and so forth. We have to look at every single coin, every 2 coins, every 3 coins together, every 4 coins together, every 5 coins together, all the different permutations of putting the coins together in different ways. That program looks like this. You'll notice that it restarts max value and max set at 0 and none each time through. I'm going to go ahead and add that print statement back in where we're printing value and set. It's useful for us to be able to see that each time through. So here, when it's checking, so we do for I in range n, so it checks sets of 1 coin, then it checks all the pairs, then it checks all the trios, then it checks all the sets of 4 coins, etc. First it finds coin 0 with a value of 55, then it finds coin 3, then it finds coin 4, then it finds that coins 0 and 3 together are worth more, then it finds that coins 3 and 4 together are worth more, then it finds that coins 2, 3, and 4 together are worth the most, and it finds no other set of coins which is worth more and comes in underweight. Now we can be confident that this is the correct solution to the problem for this particular set of coins. So the coins with these weights and these values. We know this because in carrying out a brute force calculation, we examined all of the ways that this number of coins can be put together. So we know with complete certainty that, assuming we wrote this program correctly, we have examined all possible cases. That's what a brute force solution method does for you.